Well, welcome everybody. Thanks for your time tonight. I hope I have something interesting for you. I want to talk about recurrent novae and one in particular, T Corona Borealis, that is predicted to go off again this year for the first time since 1946. And the prediction looks really good, and I'll go through that with you. Okay, so first thing, I wanted to show you what a recurrent nova looks like. You may be able to pick out which star it is. And so this is a picture of RS Ophiuchi. It went off in 2021. And the second picture is a Palomar Sky Survey picture, which goes much, much deeper. And the one with RS Ophiuchi does not go all that deep, so you can get some feel for the change in this star. The picture in 2021 was taken, I think, when it was about fifth magnitude. And so that was pretty neat. I think it made a fair bit of news, and probably some of you guys did go out and see it a couple of years ago. So, okay. So what are novae? Well, they are stellar explosions. A star rises in brightness anywhere from 7 to 15 magnitudes. So it's a massive explosion. And they're binary star systems. It's not a single star that goes nova. It's a white dwarf and a companion star that is still burning its nuclear fuel. As you know, a white dwarf is spent. It has burned off all of its nuclear fuel that's burnable for the kind of temperatures that a star of that mass can get to. And so once it has puffed off its outer layers, you just have the basically the ash of the star, the core of the star that's left. And there's no nuclear fusion going on. It just slowly cools. And the brightness that we see in a white dwarf is just the remaining brightness, the remaining heat of that massive amount of material slowly cooling down over literally billions of years. And here's just a graphic. Some of you may have been around and remember Nova Cygni went off in 1975, not too far from Deneb and not too far from the North American Nebula. So what does this binary system look like? It's pretty neat, pretty weird. The white dwarf, and I'll use my mouse here, and I hope you can see that. The white dwarf is this small thing here in the center of an accretion disk. And this is the quote unquote normal star. In truth, at this point, it's not all that normal. It is a star that's maybe later in its life. It has started to expand like our sun will as it gets older. And at some point, the mass of the regular star fills what's called its Roche lobe here, which is a teardrop shape of that star. And at that point, any mass that's here at this Lagrangian point is free to filter down into the accretion disk and start circulating around and slowly making its way down into the massive white dwarf. This is often called the hot spot here. And just to quickly explain why it doesn't filter straight on down, the answer is these are all rotating systems here. The binary rotates around, the two stars rotate around each other. The donor star here also has rotation. There may or may not be completely tidally locked in to the binary, and so there's substantial amount of angular momentum that is contained as this matter filters down, and so it's spinning along with that system, and it can't just take a straight path down. It spins its way down and slowly loses that angular momentum, just like a top slows down and finally reaches the white dwarf after some period of time. So the eruption. This is when the nova happens, and so let me talk you through this a little bit. So the donor star is bleeding hydrogen over through that Lagrangian point onto the white dwarf. As it makes its way down the accretion disk, it builds on the surface of the white dwarf. It doesn't really mix deeply into the white dwarf itself. It creates a hydrogen layer. And then as more and more mass, more and more hydrogen builds up at this top layer of the white dwarf, eventually the temperature rises to a point where you get a runaway nuclear reaction, and that's a fusion reaction. And at that point, the nova erupts. The hydrogen layer is blown off into space. And in addition to the hydrogen layer and some helium and other elements that form in that nuclear reaction, some of the underlying white dwarf material is also dredged up in this violent explosion, and that also is blown away out into space from the white dwarf. And so what's actually happening is, even though the hydrogen layer has been building on that white dwarf, after the nova, the white dwarf has actually lost mass. It's actually smaller, because not just the hydrogen is what's blown off. And by the way, too, one thing that's different between this and a supernova is both the white dwarf and the companion remain behind in a regular nova explosion. It's not so powerful that they are that the white dwarf is completely destroyed and the companion star chases off through the Milky Way by itself. So an interesting question comes about this. Some of you may already know that the white dwarfs, well, in particular, these cataclysmic variables are believed to be the precursors to a Type 1a supernova. Like I said, where the white dwarf is blown to smithereens, and the donor star flies off in its rotational path away from that area. And what we understand is happening, and why these are what we think of as standard candles that have been used to figure out the size of the universe, and Nobel Prizes were awarded for that work. The reason why we think they're standard candles is a white dwarf that gets to about 1.4 solar masses has now reached what they call the Chandrasekhar limit. And at that point, the white dwarf is no longer stable. There's enough mass there that the gravity is going to cause the white dwarf to implode. That's going to set up a nuclear reaction again, and as well as shock waves as it tries to implode, and the whole thing is blown to bits. And so the understanding is that there's a magic number where that happens, and that is this 1.4 solar masses. And it's a standard candle because it's always a 1.4 solar mass that blows up. It's a stick of dynamite where we know exactly what size the dynamite is, and it's always going to give us the same explosion. Well, okay, but I just told you that the white dwarf actually loses mass as the material filters down from the donor star and then is blown off. And so how does the white dwarf ever grow to the magic 1.4 solar masses if there are things happening before that where it gets smaller instead of larger? And the answer is we don't really know. And that's one of the things that makes this so interesting and why so many people are working on it. We've got several theories. All of them have problems. Professional astronomers around the world have been debating this for many decades now, and there is not a consensus on the answer to that question. So let's take a look at a nova. This is, well, we showed you RS Ophiuchi as it went from 0 to fifth magnitude. Well, not zero magnitude, but from quiescence to fifth magnitude. But this is the aftermath of a nova. This is Nova Persei 1901, which was not too far away from Algol in the constellation Perseus. And it is now known as GK Persei because it's a variable star. And it's also known as the Firework Nebula, and I think you can kind of see why. So this is 4 pictures put together from 1953 to 2012. And it's quite a neat animation. It shows the shell of material that has exploded off of that white dwarf, and then is swinging out into the universe. And I do have a nice color picture of it here too, taken by Adam Block at Mount Lemmon, and with the 32-inch telescope. And as you guys know, he does just absolutely spectacular astrophotography. But you can really see here all the shards, the bits, the pieces that have blown off of this white dwarf. Well, the topic of this talk, though, wasn't really novae, it was recurrent novae. And so these are a special thing. They're novae that have done it more than once. And so far in the Milky Way, we only know of 10 of those. But the proviso is, we've only been looking for a short period of time. And so there's most certainly many more than that. But of the novae that we know, and the last count I heard was about 500, only 10 are recurrent. And 2 of them have gone up recently. We've had a lot of luck with these. RS Ophiuchi, we saw the picture of that one. That went up in 2021. And U Scorpii went up, well, I was going to say last year, but 2022. And the main attraction is T Corona Borealis, that's supposed to go off this spring. So these are our 10 recurrent novae, and a lot of information here. I'll just highlight a couple of things. The brightness varies quite a bit. Let's see. RS Ophiuchi is here. It's normally around 11th magnitude, but goes to about 5th magnitude when it goes nova. And its time span between novae eruptions is anywhere from 9 to 26 years. So it's quite variable. And then we mentioned U Scorpii. It goes from about 17.5 all the way to almost 7th magnitude. And it's quite variable as well. 8 to 43 years is the gap between explosions. And then T-Pix is one that went off in 2011. This is also quite famous, and it goes off infrequently compared to some of them. 12 to 44 years. It's all the way up to 6th magnitude. But the one that is the biggest bang for the buck is T Corborealis. And this chart says it gets up to magnitude 2.5, but in truth, it gets up to 2nd magnitude. And that's what we expect this time as well. And it goes up every 80 years, give or take. And so this really should be 78 years now that we've turned January the 1st, but it's due, is what we know. And like I mentioned, was last seen in 1946. So here's what a recurrent nova actually looks like. This is a ground-based picture on the left of T-Pix, and this picture was taken in 1997. So this is the material that you see here was from previous eruptions. I mentioned it went off again in 2011. And Hubble Space Telescope somehow did just a little bit better job of the picture than our ground-based telescopes. And what's looked like it might have been waves of material or rings of material is seen much more clearly in the Hubble picture as more like globs, big clumps of material that have been blown off. And of course, this is in roughly a spherical kind of an explosion. And so most likely the blobs we see here are either closer or farther away from us than the star is. And then this is the outer portion of the sphere, just from our perspective. So why do we care? Uh, I mentioned one of the biggest reasons we care is because Type 1a supernovae are one of the most important ways that we think we know the size of the universe. And, the problem that we have is there are mechanisms in the way novae explode that tell us that they should go away from going to a type 1a supernova instead of towards it. And so something to understand. And the recurrent novae are at apparently a pretty critical stage in their evolution because they go off multiple times. But that begs the question. So are all novae recurrent, but we just haven't been looking at novae long enough to know? And Scott, I see you raised your hand. Do you want to unmute?
Yes. On the magnitudes in the previous slide, are those absolute or what magnitude are they based on?
Yeah, these are visual magnitudes. And so RS Ophiuchi was a naked eye object at about fifth magnitude, for instance. And T Corboreal is going to be quite a bright star. It won't exactly be Vega or Jupiter or Sirius, but it'll get to second magnitude, which is quite bright.
All right. Thank you.
You're welcome. Okay, so I had to show you this picture because these two pictures, because I think this is just really pretty amazing. M101 is quite the special galaxy, in my opinion, because it's had two supernovae in just the last few years. So in 2011, we got a supernova here. 2011 FE was the name given for it. And that was a type 1a supernova that we've been talking about. While just 12 years later, the galaxy gave us a second supernova. This one, on the other hand, was a type 2 supernova. And so this was a single incredibly massive star that collapsed and then exploded as it tried to collapse. And so same galaxy, two different types of supernovae. It's the ones on the left, the type 1a, that are our standard candles. And so astronomers, based on the fact that this reached 10th magnitude, can tell you how far away this star is and how far away the galaxy is that the star is in. So on to T Corboreal. This is the exciting one. The last eruptions were seen in 1866 and 1946, and so there is your 80 years. Although just recently, Dr. Brad Schaefer, who is a astronomy professor emeritus at LSU, has gone back in the literature, in monastery documents and that kind of thing, and he has found quite convincing evidence for two historical eruptions of T-Core Bore that were recorded at the time, one in 1217 and one in 1787. And those line up pretty well with the 80-year expected period. And so Dr. Schaefer, who is pretty much the world's foremost expert on recurrent novae and T-Core Bore in particular, has predicted that T-Core Bore is going to go up a little early this time. Rather than 2026, which would be 80 years, he says it's going to go up this May, plus or minus about a third of a year. And so it could go up any day now. And so some particulars on T-Core Bore. It is, well, I'll go to this one first. It's about 2,500 light years from Earth. Relative neighbor in the grand scheme of things, but not a super close neighbor. The white dwarf is not too far away from that Chandrasekhar limit we talked about. 1.4 solar masses, give or take, is that Chandrasekhar limit. And our best measurement of the size of this white dwarf is 1.37 solar masses. And there's several different kinds of white dwarfs. And this particular kind is an oxygen neon magnesium white dwarf. And so what that means is the three different kinds are a helium white dwarf, a carbon oxygen white dwarf, and an oxygen neon magnesium white dwarf. And we talked about how these white dwarfs are basically the dead cores, the ash of a star that has lived out its life. And so depending on the size of the original star, the amount of fusion that went on in this star varies. And so a star with fairly low mass would only get to the point where it could fuse hydrogen to helium before it would die and become a white dwarf. A somewhat larger star would go as far as fusing hydrogen all the way up to carbon and oxygen before it died. And so its core would be carbon and oxygen. And then an even larger original star would go as far as fusing to oxygen, neon, and magnesium before it died. And so we get these three different flavors, these three different compositions of white dwarfs. So anyhow, the red giant, in this case, it's a red giant that is the companion to T-Core Bore. The estimates on the mass of this are uncertain. I've seen numbers as low as 0.7 and numbers as high as 1.1 or 1.2. And the best estimate, well, let me say it this way. Dr. Schaefer says it's 0.8 solar masses. So I'm going to go with his estimate. And these two stars orbit each other in 228 days. And so, what is that? About 2/3 of the year is the time for the stars to go around each other once. And they're separated by about half of an AU, astronomical unit. And so about half of 93 million miles. So about 50 million miles, give or take. So that's the details on it. But here's what it has done. And this is a slide that from a paper that Dr. Schaefer put together recently. And he has gone out and grabbed the brightness measurements of T Corps all the way back to 1855. Here's 1855. This is the 1866 explosion, where it got all the way to second magnitude. It did it again in 1946. Now it only shows third magnitude, but I think that's because we got on it late to get to see that. And I should tell you too what the data points look like. So the green data points are visual or V-band photometry measurements. So this is what's going to look like, what the brightness is going to look like to your eye. And the blue dots are blue filtered photometry. Some of this is done by amateur astronomers. Is that a question? Some of this was done by amateur astronomers. A lot of these data points were actually gotten by Dr. Schaefer, who goes back into the Harvard survey plates and measures the brightness off of those plates to get this historical data, which is pretty neat. But so let me show you a couple of things that's going on besides just these massive peaks. For one thing, it's always fainter in the blue magnitude than it is in visual or green. And then just before the nova explosion, there's this odd brightening that's easiest or at least most prominent in blue filtered observations. And just before the nova goes nova, it dips back down substantially towards back where it was and then takes off. And then it does some more strange things. It doesn't come all the way back down. It comes down to a brighter magnitude, but not all the way to its normal brightness before it continues doing that. And so you can see the after behavior in the data after 1966. Unfortunately, we don't have any data from before 1866. You can see it go up, back down, off, and then over in 1946. Well, so here's now. This data actually is through, let's see, 16, 17, 18, 19. And so this is, maybe that's 2020-ish, but back around 2015, 2016 is when we saw this rise that parallels what happened in about 1936. And so you can actually go back and look at sky and telescope articles and stuff on the web, and there's a lot of discussion about, oh boy, T Corps is starting to do something, call for observations. And so let's look at that in a little bit more detail. I've blown up, let me go back. I've blown up this last little bit. And when they say what I really mean is I borrowed this slide from Dr. Schaefer. And so this is the green or visual measurements, and this is the blue filtered measurements. And this is from the start of 2021 until this slide is through, I think, about September, October of 2023. And there's a couple things you see. The one funny thing is this sinusoidal behavior. And that's an understood phenomenon that's called ellipsoidal modulation. And what that really is the secondary star, the donor star, is teardrop shaped because of the way the white dwarf gravity is pulling on it. And so as those two stars rotate around each other, at times we see the teardrop like more face on to us. I'm not sure what the right words are, but where you see it as the teardrop, and so you see much more surface to it, and so it's brighter. And then as it goes around its orbit, then it goes into a position where we basically see it as circular or spherical because of the orientation. And that's all it is. That's why the brightness does these modulations. And if you look at the calendar, you'll find that you get one, two, and back down two occurrences of this in the magic 256 days. I forgot the exact number, but in the orbital period. And so this is actually one of the ways that we know the orbital period for the star so well, is because of the teardrop shaped star's rotation. Okay, so the second thing to see, though, is if you look out here, particularly in the blue, around March of last year, it started going faint. This is that pre-eruption dip. We're quite certain. And so, again, going backwards, we're here. It had been here for about 4 years, and now it's starting to drop. And you can see that quite clearly, I think. And so I have gone out and I have pulled the latest and greatest AAVSO data. I updated this slide this afternoon. And as a matter of fact, let me go back and forth again a little bit just to help you see this. So Dr. Schaefer's slide, you got the one low spot here and then a long drop and then back up. And that's the middle of last year. And so here's the long drop back up, a long drop again to about the middle of last year. And this is what it's done since then. And so it's still very faint. It's still the drop is still there. It's still doing its ellipsoidal variations from the teardrop star rotating. And what we don't absolutely know is how long it's going to do this. If you look at the data from 1946, it's about a year, give or take. And so if you believe that it was March, let's see, if it was somewhere in the time frame of March to May last year when it started the drop, then that tells you about March to May-ish this year it's going to go. Now, in fact, we don't absolutely know whether it's going to perfectly emulate what happened in 1946, but clearly it's doing an awful lot of the same kind of thing that did in 1946. And so just FYI, the last data points, we know that it didn't explode based on Thomas Tordai's data from Hungary. This is his blue filtered data point last night at 10:18 p.m. our time. And then Louis Cason got a visual estimate of 10.5 at 4:45 this morning with 10 by 70 binoculars. And as of about 4 o'clock this afternoon, that was the last data point that I saw. One thing I should mention, though, too, is everybody's looking at this. You can see all of the data, all of the work going on. The professionals are all ready to go, ready to trigger to start working this star. There are multiple professional observatories and satellites around the world right now that have targets of opportunity proposals approved, that when T-Core goes off, they're going to rotate the dome and pull the telescope over and start doing spectrographs and photometry and radiometry and everything else they can do. And of course, up above the Earth's atmosphere, we'll have multiple telescopes going for it over multiple bandwidths. And so it's amateurs like us who are going to be the ones who see it go off and let them know it's time to trigger the observations. And I will tell you that Dr. Schaefer did a presentation specifically on T Corbor for the AVSO several months ago. And it was a really great presentation. It was about an hour long. It's available on YouTube. And if this is interesting to you, I'd highly recommend it. He goes into a lot more detail. And like I say, he's quite the charismatic speaker. He also talks about finding those two previous eruptions of T Corbor in historical documents. Excuse me. I'll mention too that the AVSO has had many, many, many video seminars and that kind of thing, and quite a few of them are available, just open to anybody who wants to go watch them. The YouTube channel is AAVSO HQ, and so that covers interesting stars, how to do photometry, how to set up observatories, all kinds of different things. Okay, so as amateur astronomers, where do we look? Where does this thing go off? And so this is a graphic from Sky and Telescope that's quite nice. It's in Corona Borealis. Right now, that is an early morning constellation. You saw that the guy submitted a U.S. measurement at 4:45 a.m. That's because it's a morning object. And so this is the ring, the crown, Corona Borealis, the northern crown. Over here is T Corbor. And then these numbers here, 83949879, these are the magnitudes for those stars with the decimal point omitted. And they omit the decimal point when you do this because it would look like a star. And they have also shown us where another really great object is. R Corbor is in the middle of Corona Borealis. And this is a really fascinating star for a completely different set of reasons. But here it is as well. If you're going to grab some binoculars and look at T Corbor, you might take a peek at R Corbor too. It's quite the red star, and every so often, we believe it puffs off giant dust layers, and the magnitude dives anywhere from 5 to 8 magnitudes before it then starts recovering. And so these are some comparison star magnitudes that you can use when looking at that. And just to give you a hint too, so if you're looking at T Corbor in the sky, this will be Boötes over here to the west, and this would be Hercules over here to your east. And Corona Borealis is quite the nice constellation. It's quite easy to pick it out if you haven't seen it before. If you want to be sure you're picking it out amongst all of those stars, this is an AAVSO chart. Now, this is one that's meant for a telescope. And so east and west have been reversed. And in this particular case, north and south have been reversed too. And so this star right here is actually this star in Corona Borealis. And I could show you 37 different variations of this chart, but what I would say is if you go to the AVSO website, you can make a chart of any size that you like. This one was a 2-degree field of view with a limiting magnitude of 12. These are all comparison stars you can do to estimate the brightness of T Corps with the decimal points omitted. But you can generate a star that's appropriate to your telescope and to the directionality that your field of view would be, whether it's inverted or not, for instance. And what I'd invite you to do is to report your observations to the AVSO. This is how the pros are going to get the message that T Corps has gone off. And so you can either do visual estimates with a pair of binoculars, although if it's second magnitude, you will not need the binoculars. Or you can do CCD, CMOS, or DSLR photometry if that's something that you like to do. And if you want to do the visual estimating, it's not that difficult. A number of folks in the club are regular AVSO contributors with visual estimates. And there's kind of a how-to, which gives you a few test stars to try out and get a feel for how this is done at this website. Once you've read through this little presentation on the website and done a little bit of trying it out under the night sky, then you just send an email to the AVSO and they will send you your official observer code. Mine is CWT. So this is me here. You don't actually have to be a member of the AVSO to get an observer code and to submit your data. We would really just love to have your data. And you can submit your visual estimates of T Corps on this web form. So you would call it out as visual, you'd call it out as T Corps, the date of your observation within a minute or so, your magnitude that you estimate, and then which stars you are using as your comparison stars. And that's how you submit it. And then if you're really interested in this stuff, and I admit I am, there's something else you can read on the AVSO website. Dr. Schaefer, I guess a couple of years ago, was kind enough to put together a list of things that amateur astronomers can do to contribute towards recurrent novae science. And so there are 6 different things that can be done. These are the 10 recurrent novae. And so you can do anything from eclipse timings, or you can do photometry to watch for super flares on this recurrent nova V2487 Ophiuchus, and lots of other things that are an opportunity for amateurs like us to contribute. And that's it. I hope I gave you a little insight into what's going on there and have you excited about seeing this nova that we know is going to go up sometime in the next maybe 6 months, maybe tonight. Thank you.
Hey, Walt, this is Bill Spizzeri. I have a question.
Sure.
Early in the presentation, you mentioned that certain, I think it was a white dwarf, had a certain mass. And I wondered, are you basing your mass numbers there on the luminosity or the orbits?
I am basing it off of reading it out of a paper, actually. Yeah, it's almost certainly not luminosity, because with cataclysmic variables, most of the luminosity, and it depends, but very often most of the luminosity is actually from the accretion disk. And so the orbit is going to be the most critical thing to understand what the mass is of the 2 components. There's other pieces too. Some of these cataclysmic variables actually eclipse each other. and so you can get additional information. For instance, some of them, the donor star is actually large enough to completely hide the white dwarf and the accretion disk when they're behind it. And so when that's the case, you can get a clear, specific brightness for the donor star.
Yeah, I can see with the accretion disk, luminosity would be a very messy number.
It really is. It really is. But one of the cool things though too is oftentimes these white dwarfs have you could call it structure, hotspots, that kind of thing.
Oh.
And so it's possible to determine the spin rate of the white dwarf itself by watching these small periodicities in the cataclysmic variables. As a matter of fact, one of them, DQ Hercules, that white dwarf spins every 73 seconds.
Yikes. Yeah,
and you can actually see that in the data. I've seen that in data that I've taken out in Columbus specifically to look for that. It's shockingly easy to find, really. So.
Okay, you're making me dizzy. Thank you, Walt.
Yeah, you bet. Thanks, Bill. Other questions?
Another question. Yeah. You can go ahead and unmute and ask your question there. I'm sorry, I can't pronounce your name. Is it Kevandre or something like that? You're on mute.
I'm still on mute, Kevandre. I don't know. Can we unmute him? Don't know that we can.
He just typed in the chat that he's trying.
Okay. Was there another question in the meantime?
Yeah.
I have a question. This is Jim Hackney.
Hang on, Jim, before you ask,
okay.
Vandre, if you still can't get it to work, go ahead and type your question in the chat and we can answer it there. But we'll let Jim go first. But
okay.
Go ahead and just type that if you still can't get off. Go ahead, Jim.
Hey, Jim.
Just a quick question. Well, on the magnitude chart, the one that was zoomed in at the end, had all of the periods. And you had visual and blue. It looked like there was a time when the blue was completely out of phase with the here we go. It looked like there was one where the blue was out of phase.
Like this one, for instance?
To the right of there. Next one. Next peak.
Yeah, no, you're right. I mean, this looks like a peak here when it's almost closer to what should be the trough. And it's there is more going on than just the ellipsoidal modulation here. There's also the accretion disk itself flickers and has a structure that brightens and gets fainter. There's what they call the hot spot, where the material hits the accretion disk. And so all of those things, plus just imperfect photometry, you can see our error bars here, make these curves really a little ratty. As again, that was something Dr. Schaefer had mentioned. Yeah, they're kind of ratty. They're not perfect. But if you phase the entire data set for T-core Bohr, you can see these curves really, really nicely. And yes, they're noisy, but we can lock in on the orbital period to like it's 250 something days plus with 4 decimal places accuracy. So I hope that explains it. Partly observational issues, and partly that there's a lot more going on than just the ellipsoidal modulation.
Very good. Thank you.
Yep.
Okay, so I'll go ahead and read Vandre's question from the chat. He says, "What are we looking for when we look at the nova? A specific pattern or explosion?" Because I'm very new to this, so I don't know much.
Yeah, that's a good question. As far as contributing, what we would want to do is just get a brightness estimate so that we can add more points. Let me go back. Too far back. So that we can add more points to these curves. Now, maybe this one isn't the right one to show you either. This is the blue filtered curve. Let me hang on here. Okay. Well, here we go. Okay, so this is the AAVSO website. I hope you guys can see my screen. Yes?
Yes,
Yes.
you can.
Okay, so this is the AAVSO website where I have called up the recent data for T-core bore. And what I wanted to show you are these black circles here. These are eyeball estimates by amateur astronomers like us. And in particular, and by the way, the green boxes are CCD or CMOS photometry. And what I want to really draw your attention to is, boy, the visual estimates are great. I mean, there's a little more scatter to them than if you're using the CCD on a telescope. But what we can do is, and we haven't done this here, but if you average them together, they draw an amazing curve that lines up very nicely with the visual photometry. And so your visual estimate of the star's brightness at any one time is what's really helpful. If you look at the dates here, so this is April of last year, July, October, and so it's varying pretty slowly. And then as far as just amateur astronomers, what we want to see is we want to see this star explode. We want to see it suddenly go from a 10th magnitude thing that you need a decent pair of binoculars to see, all the way up to a 2nd magnitude star that's easy to see with your naked eye. And so it's nothing really more complicated than that. Hope that answers your question. And let's see, I'll get the slides back here. Okay, other questions? Okay, well, thanks everybody. I really appreciate it. I will say that I'm very happy to help folks who are interested in doing this. There's some other club members who do visual work, like I have mentioned, who would love to help somebody learn how to do this. It's something that you can do for the rest of your life if you get interested in it. We have quite a few folks in the club doing it. As a matter of fact, if you don't mind, I'll send a shout out to Chris Ober and Joel Brewer and Bill Kowalczyk, because those are 3 guys that when I can't be out in Columbus to run my observatory, if they're out there, they're kind enough on a clear night to push my roof back so that I can still run it from Baton Rouge. And on this beautiful night tonight, Chris Ober has pushed my roof back, and I am working the cataclysmic variable even as we speak. So anyhow, thanks everybody.
Hey, Walt, real quick, once we started going into that, I actually thought of a question.
Yeah.
I don't know how smart of a question this is or not, but is there any chance that this thing actually goes type 1 supernova anytime soon, or is that kind of more of a long-term?
Yeah, the real answer is we don't know. But I think the answer is almost certainly not.
Yeah.
It's been doing this for we don't know how long, at least since the 13th century was when the first one of these is recorded. And as a matter of fact, we can't even figure out how it gets from 1.37 solar masses to the 1.4 that's required. And so I would say it's very unlikely, but with the help that we can give, maybe we can give a whole lot better answer to that down the road.
I think Kavandre. Oh, sorry. Kavandre was asking how he can join. So maybe one of you guys can give him the links and stuff.
I'm sorry. Was that Joe?
Yeah, sure. Yeah.
Yeah.
Yes.
If anybody wants to email me separately afterwards, I occasionally post things on the HAS email group, and so my email is included there. So feel free to shoot me an email, and I'll give you a call if you like.
I think there's one more question in the chat we missed at 7:57 from Gregory. When the nova goes off, how big is its angular size?
Yeah, that's I guess the question that comes from that is, when do you mean? When it initially goes off, which must be what you're asking, the hydrogen layer on the white dwarf, I don't believe is terribly thick, but I admit I don't really know that answer. I don't know the diameter of the white dwarf for sure either. That's not something I looked up. It should be, for a white dwarf of this solar mass, it's on the order of the size of the Earth. And so if I were just to make a guess, and it's only a guess, maybe the hydrogen layer, when it finally gets hot enough to explode, is something like the thicker part of the Earth's atmosphere. And I'll tell you what, let me see if I can't find a better answer offline, and then I'll send something out on the HAS email list about that. Okay. Let's see.
Thanks for the presentation, Walt.
You're welcome. So, okay, Stephen, I'll stop sharing and throw it back to you. Thanks.
All right. Thank you. Thank you very much, Walt. And so I'll just pop this up right here. Our next month's meeting, we're going to have the novice meeting on Thursday, February the 1st at 7 p.m. The next general meeting will be following day as usual, Friday, February the 2nd at 7 p.m. Visit us at astronomyhouston.org for registration details for the next meetings. And of course, if anyone on this call is not yet a member, you can go to the website there and join. And of course, you can visit us on all the socials. All the information you need for that is also right there on the screen. If nobody has anything else, we will go ahead and adjourn. Clear skies to everyone. I know you got some right now, so if you're not already, you don't already have your equipment imaging right now during the meeting, like some of us, get out there and do some observing.